Hi, everybody. My name is bozhi. Thanks for attending my presentation. And our study topic is why an Android app is classified as malware towards malware classification interpretation. First of all, let's look at the table below. We can see that most machine learning-based methods achieve a detection accuracy of more than 90%. We have to say that the detection accuracy is indeed very high. However, all these methods only output a binary label. In some scenarios, this is not enough. People need to know why an app is classified as malware, right? To address these problems, there exist several potential solutions. Trapping and gradient-based methods are two approaches used in Android malware classification interpretation. Line and learner are two general methods used in many fields, including image classification and cybersecurity. However, all these methods have some shortcomings, leading to poor interpretable results. For example, trapping actually outputs the features with the highest weights in the classifier rather than the test sample. The feature weights of different test samples are always the same. Line utilize linear models to approximate the locally nonlinear decision boundaries in the original model, which can easily make mistake. Learner and the gradient-based method treat the model as a black box and obtain features weights through approximation, which will inevitably introduce deviations. Inspired by the existing methods, we think there are two major challenges. One is that the feature used in Android malware detection are usually highly correlated, and their weights should not be evaluated by linear models. The other is the usage of linear models to approximate the original model inevitably introduce deviations. So to address these challenges, we propose a method called XML. The main idea of XML has 2 points. One is that XML customize the attention mechanism through a fully connected network to learn the correlation between features and then assign corresponding weights to features. The other is instead of using model agnostic methods to explain black box models, we propose an white box to identify malware and interpret the classification results, which can avoid deviations. From these slides, we can see XML consists of 2 major components, classifier and interpreter. Classifier components extract APIs and permissions from the apps as input, and then feed them into the embedding attention layer and MLP layer to predict whether the apps are malware. The classifier can also pinpoint the key features that are most related to the classification result. The interpreter component will convert the key features into the semantics and then use the semantics to produce descriptions based on ordering rules so as to interpret why an app is classified as malware. For these slides, we can see that the classifier consists of customized attention layer and MLP layer. It captured the correlation between features by formula 1 and calculate the weight of the features by formula 2. We can see that the weight of the features are obtained directly from the embedded attention layer rather than approximation. So there's no deviation. Then the interpreter the interpreter generates malicious behavior description for malware. It mainly consists of two phases. The first phase is to match the most weighty features with semantics based on their functional descriptions. The second phase is to convert the semantics into malware descriptions based on ordering rules. We also conduct experiments to answer three research questions. The first one is, can XML achieve high detection accuracy in the malware classification? Since the malware detection accuracy should be high enough, otherwise the interpretation will be meaningless, right? However, the ground truth and the generating malware descriptions by XML unstructured text, and the evaluation may be biased by our subjective opinions. Therefore, we desire quantitative analysis and a human study to evaluate if the generated description match with the ground truth. In quantitative analysis, the quantitative method, the results, we define a mental behavior as a concept. We extract concepts from the ground truth and generating malware descriptions, and then compute how many concepts in the ground truth can be detected by the XML. In human study, the quantitative measure the quality of the result. We define the rating scale as 1 to 5, where higher score means that the generated results match the ground truth better. You can see part of the questions in the human study survey in the table 7. Okay. Through the experiments, we find that XML achieve a detection accuracy of more than 98%, higher than Harbin and Lime. This lays a solid foundation for subsequent interpreter evaluation. We can see from the figure 8, the quantitative experiment shows that malware description generated by XML can match the ground truth well. From figure 7, the human study shows that the generated description results are better than acceptable and close to good. Okay. We also compare XML with Harbin and Lime through quantitative analysis. We can see in figure 9, XML achieve better interpretable results than Harbin and Lime. In summary, we have proven the good performance of XML in classification result, and classification accuracy, and interpretability. However, it still has some limitation. One is that XML only use APIs and permissions to identify malware and interpret classification results. I think more types of features should be taken into consideration, right? The other is XML cannot detect the malicious behavior when the malicious payload are only introduced by native code. This is because XML only use APIs and permissions to identify malicious behavior. So I think all these limitations need more work to serve in the future. Okay, that's all. Thank you.
Hello again to everyone. The next paper of the session is why an Android app is classified as malware, towards malware classification interpretation. One author is bozhi, who is here to answer any questions you would like to ask. So please use the chat to ask any question you would like. So my first question is, how do you classify into benign and malicious? What's the difference for you?
Okay, please, I will share the screen. Okay, share the slide. Wait a minute. Can you see the slides in the screen?
Yes.
Actually, we first of all we extract the API and permissions from apps as input, right? And then we feed them into the embedded attention layer and MLP layer to predict whether the app is a malware or not. The classifier can pinpoint the key features that are most related to the classification result, and we will get the weight of the features by the attention layer, and then use the weight of the features to add to multiply with the multiply by the value of the feature, and then use a MLP layer to map the layer to the two class benign or malware. Yeah, that's a simple model. Yeah.
Okay, and have you seen some features that are difficult to be classified in both groups? Because sometimes this classification is not so objective. I mean, maybe the concept of malicious in some sense is subjective and depends on some context or on some subject. So have you considered or have you identified any features that are difficult to be classified in any of these groups?
Actually, I can't remember the details, but I do remember there exist some features that exist in both groups. They, for example, the message send message the permission to send message will be used in both the malware and the benign app samples, right? Because some benign apps will use the permission or the API to send message. The malware will also do the same things. So these features is very difficult to use. It's not easy for to be used to classify the malware, but they can be cooperate with other features to classify the malware. For example, if one application use the API permission as well as some permission as well as some permission that first, if the model used some permission like hidden from the users, hidden from the users, that will that means the application will very likely to be a malware. So one feature is difficult to use to classify the application as malware or not. They have to cooperate with many features to determine whether the application malware or not. That's the reason why we use the attention layer. That's why we use the attention mechanism to interpret the classification result. Because for example, the line and the drag bin, that method try to understand the model. Try to understand the classification result with a linear model. But actually, the features used to classify the malware are highly correlated. They are highly correlated. So we cannot use a linear model to interpret the classification result. So
Okay.
okay.
My next question is that you recruited many persons from industry in your experiment. And it's not easy at all to do it. How do you manage to recruit so many people for the experiment?
Okay, actually, we cooperate with a team of security experts from the National Internet Emergency Center for a long time. They are good at malware analysis. They're good. They work. They work for that. Their work is to analyze many malware.
And how
So
do you combine them? Did
yeah.
you give any prize or any money? I don't know.
Yeah.
Did you invite them to for a dinner or something like that?
Our research will share with them because they also need the research. They need to because now they manually analyze many malware. This spend a lot of time and and money, right? If our research can help them to understand the malware automatically and reduce the manual label, that will be very good for them. That will be very useful for them. So they would like to spend their effort. So they, of course, we need to share Simon with them, and we will share. They will share the data with us, and we will share our research result with them. That's a cooperation. Yeah.
Okay, so thank you very much, Bozhi.
Yeah.
If there are no more questions from other attendees, I think we can finish here the session of question and answers. So receive a virtual clap for all the attendees.
Thank you.
Very nice work. So see you in the next session.
Okay. 谢谢，
Bye bye.
拜拜。